Hi. Now, as an example of what we have just said about the relation between ensemble and single systems in quantum mechanics, let us take a brief note on the Schrödinger-Cat-Gedanken experiment. Let us assume the usual situation in which we have a box with some kind of random system, which is here. We have here a system that can trigger the action of this hammer, and this hammer will break a vessel in which we have venom, killing if it breaks, or not killing the cat by the release of the venom. Of course, we assume that there is some percentage related to the triggering of this apparatus. For instance, we may assume that we have 50% of chance of triggering the hammer and thus 50% of chance of killing the cat. Of course, the box is closed. We don't know what happens there. And the usual interpretation says that in this case, because we are not seeing the situation, we are not seeing the cat, the state of the cat is indeed in, with respect to quantum mechanics, in a superposition of states that are live and dead. So we have a cat that is, in a sense, live and dead at the same time. This is the usual approach to the case, and of course, in this approach, what is important is that we assume a single system. But is this appropriate? This is the question that we are interested here to answer. Let's assume first the ensemble interpretation of this situation. In this case, we don't have one box with cats and venoms, etc. We have in fact an infinite number of similarly prepared systems, cat systems if you want, exactly in the same situation, initial situation, and in some of these systems the triggering apparatus will indeed release the venom and kill the cat, probably in 50% of these physical systems, equally prepared physical systems, and in the other 50% of them there won't be any venom released. So in 50% of them we will have an alive cat, and in the other 50% we won't have that, we will have dead cats. So the ensemble explanation is pretty much obvious. It represents an wave function, psi, of the total system that is related indeed to dead and alive states, but each one of these probability amplitudes are related to the possibility of a single situation, a single system, which is the cat being dead, or exclusive, or the cat being alive. Of course, we may assume that we use this probability amplitude to make the density, probability density, and thus we will have to take into our considerations the four coefficients that appear in the density function, which is our observable. In this case, we have the first case, which is C1 squared, which represents the probability of finding the cat dead. We have the C2 squared as the probability of finding cats alive. And we have these two situations here, which in the single system approach will represent the probability of finding the cat in some sort of superposition of dead and alive state. Of course, in this interpretation, the ensemble interpretation, there is nothing like that. The first two interpretations are similar, of course, but this one here represents only the correlations that this apparatus introduce in the problem relating the two states, the dead and alive states. These states, of course, when we look at the Hilbert space, they are orthogonal. And then when we integrate, these two terms are zero, of course, and we get only 50% or one half for each one of these coefficients here. So the interpretation of the ensemble interpretation of the problem is very easy. It has no weirdness in any sense. Of course, we may now assume, based on what we have said about the ergodic principle, if the ergodic principle is possible to be assumed here in this example. And the answer, of course, is no. We can assume that because this kind of experimentation, this kind of Gedanken experiment, does not have any structure that allows us to apply the ergodic principle. And this is obvious because the ergodic principle here won't be applied because the cat, at least in some situations, will die. And after the cat dies, we can restore the system to the initial situation and then perform another measurement in the situation. We know that death is a quite destructive situation, experimental situation, and then it will be impossible to use the cat to make uh, measurements live, dead, live, dead, live, live. It's not possible, of course. Whenever the cat gets dead, it won't get alive again. So we if we want to assume a single system approach, the fact that we cannot restore the system to the initial situation is quite crucial here because we, in such a destructive kind of experiment, we cannot make any sort of assumption regarding the ergodic structure of the problem. So, in fact, what we are seeing here is that the weirdness that comes from the interpretation of this problem is not related to uh, the fact that quantum mechanics itself is weird approach to the nature. In fact, what we are having here is that we are trying to apply to a system that have a different time structure the ergodic principle that because of this structure is not applicable. Okay, let's see another example of the same situation now with experiment that's not that controversial. Let's see what happens in the double slit experiment, for instance. Of course, we have here the same thing. May have a single system picture or an ensemble picture. It begins with the ensemble picture, in which we have in the beginning a number of particles that are incoming from the left, and these particles that are sent each one at a time, of course, pass the slits and hit the screen at some point here. Of course, each particle in this interpretation will hit a different point in the screen, and after the sent of a number of particles, which will constitute the ensemble of this situation, physical situation, we will have the interference pattern which is presented here. So the interference pattern is related to the ensemble. It's not related to individual elements of the ensemble. Of course, this is one interpretation, but if we try to force the single system interpretation into this situation, what will happen? We will have here in the left of the experiment an incoming set of physical entities. We don't know if these entities are can be represented by waves or particles, but we assume that they are waves indeed. The, these waves pass through the slits, interact with itself, and hit the screen, the detector screen. But when it this extended entity, which is a wave, hits the screen, what happens is it is that it in some way comes now as a individual point in the screen. So we have to explain how this extended entity, which is a wave, now transforms itself into a single point in the screen. We have this, of course. We have this explained in the usual interpretation by the notions of duality and the reduction of the wave packet. Indeed, what happens here is that for some reason this extended element reduces as a wave packet to a point in the action of hitting the screen. But if this is true, of course, we have here a situation in which presumed particles are indeed represented by waves, at least in this experiment. While in other experiments we have, of course, the corpuscular picture valid, so we must assume that there is in the realm of quantum mechanics some sort of duality. But here, again, we are trying to force a single system interpretation into a situation in which the ergodic principle is not applicable. And it's not applicable because, again, this is a destructive experiment. This experiment cannot be done with a single system, that is, with one system that is sent by Sanovan into the slits and then hit the screen at some point, because when it hits the screen the experiment ends and cannot be restored to the initial situation. So this kind of destructive experiment cannot blocks, in a sense, blocks the ergodic interpretation, ergodic principle. We cannot assume the ergodic principle here, and because we cannot assume the ergodic principle, we cannot interpret this situation, this experimental situation, by means of a single system. Thus, this kind of situation, which is kind of a weird situation, appears not because quantum mechanics is weird, but because we are trying to force an interpretation that makes it weird. It's a problem again related to our intentions of making this kind of interpretation based on single systems when it is not applicable in any way. Okay, let's see in a case in which the ergodic assumption can be indeed used. In this case, we assume here that we have an atom, any kind of atom, for instance, and this atom, the electron of this atom, or the electrons, if we have more than one, are performing trajectories around the nucleus, and these trajectories are random, as we can see here in the picture, and they are random because there is a exchange, as we have already seen, between the corpuscular system, represented here by the electron, and the electromagnetic subsystem, related to the electromagnetic radiation around the nucleus. So we have this situation, and of course we can perform our measurements into this atom to see at each instant of time, for instance, the position of the electron. We can measure that. We can measure that in another instant of time. Of course, we are giving the atom sufficient time to relax to the original situation, though, so we are not performing a sort of experiment that will, for instance, make the atom to emit the electron, which will forbid us to make another experiment in the same situation. And thus, we, assuming that we are not doing this destructive kind of experiment, we may make the same experiment along the timeline a number of times and then make our averages. So, in this case, we may apply the ergodic assumption, and the fluctuations will, if the ergodic assumption here is applicable, the average time average will give exactly the same result if we have a number of identical systems prepared, identical set of atoms, and we perform at a single time the the infinite number, of course, ideally the infinite number of measurements in each one of these experimental setups. So in such cases, of course, if the experimental situation is such that we are not destructing the initial system, which is the atom in this case, we may apply, at least at this point, we can say that we may apply the ergodic principle, and the single system picture is clearly applicable. So we are not saying that quantum mechanics is not applicable to a single system. What we are saying here is that we know, because of the demonstrations, that the quantum mechanics is always applicable to ensembles. In some situations, depending on the way we make our experimental setup and the way we make our measurements, we can perform these measurements along the timeline, and the ergodic assumption will guarantee us that the averages that comes out of this kind of approach, the time average approach, will give exactly the same results as the ensemble approach. So what we are saying, summarizing what we have said, is that in some situations in which the experiment is not a destructive one, we can, of course, change between the ensemble and single system interpretation seamless. But in some cases, the kind of experiment we are performing blocks us the application of the ergodic principle, and then if we, in such case, try to force a single system interpretation, we end up with very weird situations. This is what we would like to present. In the next video, I will bring the discussion of the interpretation of the dispersion relations, Heisenberg dispersion relations, in the realm of this approach. Thanks for watching.